Students, hello. So, I have started semiconductors yesterday, and I'm just flashing the slides. I hope what is electronics, active components, passive components, and a brief introduction to SE, bond breaking, and band theory, etc. we have discussed in the last class. Okay, then we have also understood that in semiconductor, of course, you can explain the conduction in metals, insulators, and even semiconductors using band theory. And here for semiconductors, we have something very interesting. That is, there are two types of charge carriers, and how those charge carriers emanate, that is best explained by this energy band theory. And then yesterday we have seen we can classify based on the band the energy cap. Basically, we can classify it into three categories: conductors, semiconductors, and insulators. I think till this we have discussed yesterday in detail. And well, the concept of hole also has been discussed yesterday. Now just understand that when electrons, see, each electron has been designated by a particular energy level. Just like in a isolated atom, you have got same thing here. Okay, right? So Pauli is exclusive principle for isolated atom. Pauli is exclusive principle for the atoms in a material. Okay, they're all same, right? But so every electron has been designated by a energy level. Let's understand. So now here, as far as the valence electrons are concerned, that means the electrons which are responsible for bonding with the neighboring atoms, they become very significant, and their energy levels, we call it as the valence band energy levels. The most important thing is, due to external energy, if the valence electrons absorb the external energy, they gain the energy, and as a consequence the bonds break, and if the electrons which has come out of the bond has sufficient energy, then they move on to the next higher energy level, and that next higher energy level will be after a gap, energy gap, that what we call it as forbidden gap, and then these electrons will attain the status of free electrons. We have discussed what is the concept of free electrons. And most importantly, this electron which has left the valence band has left an empty energy level. Empty energy level, with hitherto was occupied by a valence electron, is now empty, and this empty energy level in the valence band has got capacity to attract an electron. So therefore, the process of conduction is now because of two charge carriers. See, in metals, the electrons move from one point to another point, they just move. But when they move from this position to this position, it doesn't create any empty energy level which can attract the electrons, neighboring electrons. But that happens here, and that is why the concept of hole is created. So we have got two charge carriers, electrons and holes. Okay. Now this picture also I have given in some of my lectures. As you can very well see here, this is at 0 Kelvin. You can see there are no holes. All the valence electrons are bonded, and as temperature rises, some of the valence electrons have been dislodged from their position, as you can see here, and this electron which has come out from the valence band and entered the conduction band. Important. It has come out of the valence band and entered the conduction band. Okay. So there is a hole and there is a free electron that is created. This is a schematic diagram. I think that is visible to all of you. Clear? Yes. Please keep your mic unmuted and please answer. This is one issue that we have discussed so far. Okay, now let me explain something very, very interesting about this semiconductor material. Okay, please, if you want to read, you read. I'll give you 1 minute to read. Just read this if you want. Effect of impurity. Impurity doesn't mean that some kasa, no, not that. We define an impurity as a dopant. So doping is a method of adding desirable impurity. Why we call it impurity? Because see, now if you have taken silicon substrate, it only contains silicon atoms. Now any other atom that you add to it by a process is now designated as impurity, and specifically here if this foreign atom that is added, foreign atom or atoms that are added, now if they are accepted by the substrate, right, then we start calling that impurity as the dopants. Okay, dope. Okay, we say the semiconductor is doped. That means some additional atoms not belonging to the same substrate. That is, if you have taken silicon, you are adding some phosphorus, arsenic, boron. I'll tell you why you have to add these specific things. That will become clear to you. They are called as dopants. Okay. Now, doping is a process of deliberate addition of desirable impurity atoms to pure semiconductor. Pure means intrinsic semiconductor, to modify its properties in a controlled manner. Very important. Added impurity atoms are called dopants. Impurity atom may be added as 1 part per million. So for million atoms of the parent, that is, if you take a silicon, if the substrate has got, it will have millions of atoms. So you are just adding dopant 1 part per million. The dopant atom should take the position of semiconductor atom in its lattice. That means, you see, here you have got silicon atoms, you can see. So the dopant must simply replace. The dopant must simply replace, okay, one of these atoms or many of these atoms. Okay, that is what, it will not disturb the lattice. The lattice structure will not be disturbed. That is what is meant by, it should not disturb the lattice. The size of the dopant atom should almost be the same as that of the crystal atom. The concentration of the dopant atoms should not be large, more than 1% of the crystal atom. It is to be noted that doping of a semiconductor increases its electrical conductivity to a very great extent. Very, very important. So dopant increases the conductivity to a very great extent. Okay, now read till this one. Okay, there are 2 different methods of this, alloy method and diffusion method. This just meant it. Okay, now the most important abstraction from these statements is that, you see, please listen very carefully. Now, it's the nature which has made different materials. Say it can be copper, it can be aluminium, it can be silver, many materials. Now, the conductivity of these materials. I suppose all of you remember what is conductivity. The conductivity is fixed. If you have taken copper element and if you have taken a bar of copper, the conductivity of copper is fixed. The conductivity of aluminium is fixed. Hello, are you with me? All of you?
Yes.
Have you come across something where you can alter the conductivity of, say, a copper bar at the same temperature without increasing or decreasing the temperature? Can you alter the conductivity of this material? Okay, so far I think we have not come across any theory or any sentence so far which supports that, you can alter the conductivity of a material. Am I right?
Not of that pure material, you said.
See, if you have taken copper or aluminium or steel, something, you have taken one material, its conductivity is fixed. Okay?
Yes, sir.
Can you alter its conductivity? Have you come across something like that? I'm sure you would not have come across. Clear? Hello? Yes. Now here you see, this is where you see science triumphs. Science triumphs. I'll tell you why. Human beings human beings, they were able to create materials. Listen here very carefully. Human beings were able to create materials in such a manner that they could define the conductivity. So you see here, I want to have a material of this conductivity. I'm not telling you, any range of conductivity, some small range of, different values of conductivity. I want to have a material of this conductivity. Okay. Well, you can manufacture. It's not, metallurgical sciences and different compounds are formed. We'll have different conductivities. But here what I'm trying to tell you is, you take, say, silicon, and then you say, look, this material का conductivity मुझे बदलना है. कितना बदलना है? इतना बदलना है. तो हम बदल सकते हैं. जितना चाहिए उतना बदल सकती है. ऐसा कि मतलब नहीं कि infinite. तो थोड़ा बहुत, I can vary the conductivity of this material. Okay, I suppose you have captured what I have told. Okay, so this is where we say we are the creators. Okay, there is an Almighty who has created this. That's different. Now here you see in this context, I say the human being says, I am a creator. He has been able to create material whose conductivity is under his control. Did you understand, students? Hello? Very important. Okay. So therefore, one of the important things is that, what you have to mark is, you can increase the conductivity of a material to a very great extent. That is the first achievement of the human being. Okay.
Sir, instead of increasing the conductivity of the material itself, low conductivity, sir, why can't we use metal, sir?
Wait. No, why can't we use metal and all? We'll not ask that question. See, the purpose is not to just increase the conductivity. It is one of the things that man is able to achieve. Please, it's not the purpose, it's not the goal. Okay, but one of the significant things that you have to now watch out here is that we are able to do that by a process called doping. Doping just doesn't only mean it will only increase the conductivity. It does many more things. Okay, now please understand this. What is silicon? Silicon. Where do you find silicon in nature? You have to dig deep into the earth. Okay, then you will get silicon. I suppose all of you know that, no? Hello? Do you know the source of silicon?
Sand, sir.
Silicon. The source of silicon is sand. Correct, you are right. Abundant quantity of silicon. Sand is basically SiO2.
Yes, sir.
And even Si is abundant. So you got abundant sand. So you go to the seashore or even riverbed, you can collect. Okay, you can collect sand. Okay, you can collect sand here. So one butti of sand. You process this one butti of sand. Say one butti of sand, some 50 rupees. You process it. You can convert that into mobile phone. Basically, it is semiconductor. And this would have needed something like around this much amount of silicon got from the earth. We process it. That's where engineering comes into picture. And that value of 50 rupees is now converted into 50,000 rupees. 50 rupees is converted to 50,000 per material. The raw material is very simple. Of course, the process is involved. That is a different thing. But what I am tell you is, in Kannada they say, kasadinda rasa. Okay, kasadinda rasa. I hope you know the meaning of it. So that is what, and how is it possible? That is what you are going to learn. So the first step is that we have understood that there are two types of charge carriers. Second thing is by doping, one of the effects of doping is you can control the conductivity. There are many more effects which we are going to discuss. I suppose you have some idea now. Doping, hello? Conductivity, yes. Slowly and steadily you understand. Okay, now here you see we are not only able to increase the conductivity of a semiconductor material, but we can now create two types of materials called as younger type of metals. material and P type of material. Basically it is silicon. But now they say it is silicon. This is silicon. Now I will create two categories of materials called as N type and P type of material. Okay, let's understand what is this N type and P type of material. Then you will appreciate what is all this about. Okay. See, N type of material, pentavalent impurity, phosphorus, arsenic, okay, Sb. They are called as donor impurity. Then P type of material, gallium, boron, indium, aluminum. So what is this? What is common between gallium, boron, indium and aluminum? What is common? They are all trivalent materials. And their size is same as that of the silicon atom or the germanium atom. And what is common between phosphorus, arsenic, Sb, etc.?
Pentavalent.
They are all pentavalent and their size is same as that of the size of the silicon or germanium. That is important. Similar, not exactly same, similar. They fit into the lattice, they will not disturb the lattice structure. Right? Okay. So that's a significant thing. Right. Now, let's understand this N type of material. Okay. So when a pure semiconductor, silicon or germanium is doped with pentavalent, appropriate pentavalent impurities such as phosphorus, arsenic, Sb, bismuth, okay, then 4 electrons out of the 5 electrons of the impurity, because they are pentavalent, take part in the covalent bonding with the four silicon atoms surrounding it, and the 5th electron is set free. The 5th electron, because pentavalent, you can see here, okay, there is arsenic added. So the 4 atoms, the 4 valence molecules, they bond with the neighboring things, and there is a 5th electron of the arsenic which is unbound. These impure atoms which donate a free electron for conduction is called donor. So therefore, you see here, students, the moment you add a dopant such as phosphorus or arsenic. See, this addition is different from the chemical addition. Understand? See, in chemistry you are learning the bonding. Here you see in the lattice we are replacing, we are pushing one more atom into this, one or many more atoms, and creating a structure like this. There's an important difference. So the donor impurity usually represented by Nd. Okay. So Nd stands for what? The concentration of the donor impurity. Due to donor impurity, free electrons, E minus electrons, increases very much, and it is called N type of semiconductor material. By donating an electron, impurity atoms get by donating E, impurity atoms get positive charge and they are called immobile donor positive ion. Now please appreciate this, very important. See, this arsenic, it went and sat in place of a silicon atom. See, there was silicon here earlier. This arsenic has gone and replaced that. And in the process, this arsenic got bonded with the neighboring silicon atoms. But in the process, it donated this electron. Free by दे दिया, O electron दे दिया, और O electron जो दिया, that becomes a free electron. It straight away goes into the conduction band. That's what happens. And therefore, this arsenic atom here becomes immobile donor positive ion. Immobile, why? It got fixed into it. That's why it becomes immobile. Donor positive ion. In N type of semiconductor, free electron is called free electron here is called majority charge carrier, and holes are called minority charge carriers. Okay, I'll explain this nicely to all of you. Now listen aram se and try to understand. Okay. So as you have understood most of the things here, that is when you add pentavalent substances, such as phosphorus, arsenic, etc., they get fixed into it. They donate an electron. This electron straight away goes to the conduction band. तो इसका मतलब क्या हुआ? See, even at 0 Kelvin, if you dope it with pentavalent substance, the intrinsic semiconductor no longer is called intrinsic, it is called as extrinsic semiconductor because it is doped. And even extrinsic semiconductor at 0 Kelvin will have electrons in the conduction band. Will have electrons in the conduction band. So therefore, their conductivity has increased. Clear? Hello? Their conductivity has increased. Now, what has increased? Basically, see, there are two types of charge carriers, holes and electrons. So here, what has increased? The electron. What has increased? The conduction electron has increased. The concentration of the conduction electron has increased. Now let me explain this once again. See students, if you take intrinsic semiconductor, okay, well, you have seen that band structure like this. This is conduction band and this is valence. Now, assume that there were electrons here, many electrons, and this was empty. Okay. Now, say this electron leaves here. So when it leaves here, it creates a hole, and this electron will move here. So what happened? For every free electron that is created, there is a corresponding hole created. So the concentration of holes will be equal to the concentration of free electrons. Do you appreciate that? Yes. And it's a random phenomenon. Random phenomena means, please understand. See, there will be holes generated here because this will move here. And these electrons which have gone into the conduction band, as you know, it will not stay there forever. This will try to come back to this. I think this is already discussed. Stable state, metastable state, it stays for so much time and then it comes back automatically. So there is a continuous process. Holes are created, conduction electrons are created, again this comes, again this goes. But under equilibrium condition, you will find this is always maintained. I think I have explained this dynamic equilibrium in some other context to all of you. If you have doubt, you can ask me, I will explain. I hope you understood this. Dynamic equilibrium is reached. Okay. So therefore, this will hold good. But now when you add a dopant, such as pentavalent substance, now this will not be equal. This will not be equal. Now here, Ne concentration will be greater than NH concentration. Did you understand? Did you understand? I am asking you. If you have doubt, you ask. See, you will have profound questions on this. So please understand it very deeply. Did you understand or no? Or you have some doubt? Ask.
Sir, one doubt, sir. Sir, if we have excess electrons in this case, like not excess exactly, but the electrons as charge carriers will increase in this case, then why can't they get attracted to the holes and like reduce the number of holes, sir? If that is also one possibility, sir.
See, that's what. So you must listen very carefully. Holes are created because this has moved here, and after some time this will again come back and occupy the holes. Again new holes are created. This is a continuous process.
Yes, sir.
Okay,
yes,
it's a continuous process. So you know, some electrons can which are created can again fall into the hole. It recombines, and once again they break. It happens. This happens. But at all the time for intrinsic semiconductor, the concentration of hole will be equal to concentration of free electron. Got it?
Yes.
Now when you dope it, when you dope it with pentavalent, this is what happens. This is what happens. Listen here. Listen here. See, you be a bit careful here. See, you get the mental picture proper here. See, formerly, I have drawn this band, this band, valence band, and conduction band. For every hole that is created here, there is an electron here. Agreed?
Yes.
Right. Now, when you dope it, okay, when you dope it at 0 Kelvin, you can still find an electron in the conduction band, and its corresponding hole in the valence band is not there.
Yes, sir.
So therefore, you see, this is not the picture. There will be valence electrons here, okay, and there can be many more electrons here also. But if you, at any given point of time, if you count the number of free electrons here, and if you count the number of holes here, okay, you will find that the concentration of these electrons will be more than that of holes if you have doped it with pentavalent substance.
Yes, sir. Agreed, sir. But the doubt that I had was, now we don't use this at 0 Kelvin, sir. At room
okay, wait. First you understand at 0 Kelvin. Then we'll come to room temperature. First you understand at 0 Kelvin. Did you understand this at 0 Kelvin?
Yes, sir.
Okay. At room temperature, what happens? Yes, at room temperature, they are thermally generated free electrons and thermally generated holes.
Yes, sir.
And these thermally generated free electrons and thermally generated holes, the concentration of these thermally generated electrons and thermally generated holes will be equal even at higher temperatures.
Yes, sir.
Understand? But if you take the totality of the hole concentration and the electron concentration, then this is what will be the equation. Okay?
Sir, one doubt I had in this situation, sir, in thermally generated electrons and thermally generated holes, sir. Now, sir, as you said, at 0 Kelvin, there will be some electrons present in the conduction band such that there are no corresponding holes present.
Good.
Yes, sir.
Correct.
Now, in the state, in the room temperature state, sir, there will be many things happening. So, like electrons, holes, movement, everything will be happening, sir. One of the possibilities is that the electron, which did not have a corresponding hole at 0 Kelvin, goes to one hole, and that hole does not exist anymore.
Simple mathematics and simple mathematics, man. See, very simple mathematics. You see here. Now at 0 Kelvin, assume that there is an electron here and no hole here. Agreed?
Yes, sir.
At some temperature T, there are 2 holes created here, corresponding 2 electrons are created here. Okay, now your question is, sir, this electron, will it go and get into this hole? Yes, it will go and get into this hole.
Yes, sir.
So what? The number of electrons are still 2 here and number of holes is still 1 here. So the concentration of electrons is more than concentration of holes. Because if this electron has combined here, one hole is also reduced, one electron is also reduced. So this concentration of electrons will always be greater than concentration of holes. Simple mathematics, man. Simple mathematics.
But then we have holes and electrons as charge carriers. If that is decreased, then conductivity should also decrease.
Arey yaar, boy. Listen here, yaar. Conduct what? Okay, now don't mix up things. I am talking about the concentration. I am not talking about conductivity. Did I speak about conductivity here? No. I only spoke that this is happening. Did you understand this?
Yes, sir.
Okay, first thing you understand this. See, you don't mix up many concepts. You have the habit of mixing many concepts. Okay. Now, if you want to talk in terms of conductivity.
Sir.
Sir,
after doping cell, in that equation which you gave for number of electrons moving to valence, conduction band from valence band, will that hold here also?
No, we'll talk about that equation next, after I teach you mass law action.
Okay. Yes.
After I teach you. See, that equation, it was very clear. What is that? What was that equation telling you? The number of electrons that are moving from the valence band to conduction band as the temperature increases. So that's why, I said thermally generated.
So will that be same?
Wait, listen. There are two things here. One is you will have the free electrons in the conduction band because of the thermal, because of the temperature. There is presence of free electrons in conduction band because of the doping.
Right.
There are two different things. But in totality, if you see, this happens. This happens.
So
But
thermally generated electrons, sir,
Huh.
will that be still there in that equation?
still, yes, it will be always valid. It will always be valid. Because the basic semiconductor has not changed.
Yes, yes.
But however, at this point I would like to say something. Okay? See, now there are certain energy, see, when you take intrinsic semiconductor, there are certain energy levels here, that is fixed. The number of energy levels. But when you add a dopant, appropriate dopant, new energy levels will be created. Either here or here. That happens. I will explain that later on. Correct? That happens. And when you add dopant, new energy levels are added. See, new energy levels are added. Either this is added or this is added. I will tell you later on. And this energy gap is also reduced. Correct? So when the energy gap is reduced, then the probability of an electron crossing from here to here increases.
Yes, sir.
And therefore, the concentration of the charge carriers,
Yes, sir.
concentration of the charge carriers itself increases.
Okay. Yes, yes.
And as you know, conductivity depends upon one of the important things. What is it? It is the concentration of the charge carriers. Concentration of the charge carriers. Okay, and it is also dependent upon the mobility factor, if you remember in metals. Also, Mr. Abhinav, your question is also answered here. So the concentration of the charge carriers has increased because electrons are added here, and not only that, the energy gap, the forbidden energy gap is also reduced. Therefore, the probability of the charges crossing from here to here will also increase. Therefore, the carrier concentration will increase. Therefore, conductivity will increase. Is that clear?
Yes, yes.
Okay, sir.
Good. So, you aram se ask question. You have to be very, very specific. Right? You cannot mix many things. Right? Okay, friends. I suppose you understood this.
Yes, sir.
Yes, sir.
So, what is N type of material? Come on, tell me whatever you understood. Quickly. Arey yaar, whatever you have understood, you tell. Everybody don't keep quiet there.
N-type semiconductor is an extrinsic semiconductor which is doped with the pentavalent atom. It has similar size and can fit the lattice of the semiconductor.
Consequence of that?
Due to which there is increase in the concentration of charge carriers, which increases the conductivity of the semiconductor.
One important thing you missed out. This equation, and the concentration of the free electrons is greater than the concentration of the holes. This is very important. Because of this only it is called N type of material. Clear? Very important. Okay, right. Now, P type of material. So, P type of material, you are going to dope it with trivalent impurity. Okay? And see here, when you add a trivalent impurity, trivalent. So, trivalent, what has this trivalent impurity done? So, here you see this trivalent impurity, it has got only 3 valence electrons. Correct? So, therefore, 3 valence electrons are there. Okay? Oh, sorry, this should not be shown here, it should be shown here. Sorry, hole should be shown here. So, one of this and one of this, not this, this should be shown here. This arrow should be here. So, one of this, 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 and one of this neighboring atom, but one more it cannot pair. Okay, so there, if there was the fourth electron, it would have bonded. Since it is not there, that region, that particular energy level, which hitherto should have got an electron, is empty, and therefore that represents a hole. Okay, now let me explain this. Wait a minute, don't think. Huh? So what it means is here, it has created an energy level which has got the tendency to attract a loose electron. You understand? Hole means it is an energy level which has a capacity to attract any loose electron in its vicinity. Got it?
Yes, sir.
This is not the case in metals or any other conducting material, but here it is. So therefore, when you add a trivalent impurity, okay, when you add trivalent impurity, which is called as acceptor, Na, okay, then you see it is automatically creating what is called as a hole. So therefore, when you add trivalent materials, the hole concentration will be more than that of the free electron concentration. In type, this is for P type of hole. Of course, this becomes what? An immobile acceptor, it negative ion. So in P type semiconductor, free electron is called minority charge and holes are called majority charges. In N type, it is ultra. So for P type it is this, for N type, you have got what? This is larger than this. Got it?
Yes, sir.
At any temperature. This is the basic difference between the two. Okay? Now, this is very, very important. So, my dear friends, what you have to now understand is, you have created two materials, P type of semiconductor and N type of semiconductor materials, right? And the concentration of holes here is greater than concentration of electrons. Here, concentration of free electrons is greater than concentration of holes. Okay, got it? Yeah. So you have created two types of materials with different concentration. Okay? Hello?
Yes, sir.
And not only you have created concentration, you have also, as I have also explained to you, that the new energy levels are added in the forbidden gap just below and above the valence band and conduction band, and as a consequence, the forbidden energy gap is reduced in height, and therefore the probability of creating more charge carriers is increased, and therefore the conductivity increases. Okay, till this extent you have understood?
Yes.
Now you see, by a process called metallurgical union. Metallurgical union. By a process called metallurgical union. So metallurgical union means you take a silicon material. There are different processes in brief I am telling you. You first dope it and make it N type of material. Then here in this small region, okay, you further dope it with P type of material and make this P type of material. So this you make it as P type of material and this is N type of material. So here you see you have created a junction here. Okay, you have created a junction here. This junction is called PN junction, and there is a boundary between P type and N type. Or in other words, P type is joined to N type by a process and it is called metallurgical union. देखिए, अगर मैंने एक P type मटेरियल लिया और N type मटेरियल दिया और इन दोनों को फेविकॉल लेके चिपका दिया, ओके, इन दोनों को फेविकॉल लेके चिपका लिया, इसको हम नहीं कहते हैं कि मेटलर्जिकल यूनियन. ठीक है, एक प्रोसेस के दरमियान इफ यू आर एबल टू डू दिस देन इट इज कॉल्ड मेटलर्जिकल यूनियन. गॉट इट?
Yes, sir.
Good. Now when metallurgical union takes place, okay, Now let me draw this to you in a bigger way. When there is metallurgical union of P type of material and N type of material, what happens? So here you see the concentration of holes is larger than concentration of electrons. Concentration of holes. And now if you compare these two regions, the concentration of holes here is more and the concentration of electrons here is more. Do you appreciate and agree?
Yes, sir.
Now what you call it as concentration gradient. Concentration gradient exists. Concentration gradient exists. Now, in biology, you have studied a process called osmosis. Have you studied that? Hello? Chemistry. Okay. What is osmosis? Through a semi-impermeable membrane, the substance moves from higher concentration level to lower concentration level. Correct now?
Yes, yes.
And what is this process called when particles move from higher concentration level to lower concentration level? What is that called? What is it? Excellent. Diffusion. Diffusion. Now, don't you see diffusion taking place here? Because the concentration of holes is more here and the concentration of holes is less here. Correct? Here, the concentration of holes in this region is less. Here, the concentration of holes is more. So, therefore, the holes have a tendency to cross here. See, now there is a difference between diffusion and drift current. Hello? It is the hole concentration here is less than the hole concentration here. Therefore, the holes will move from here to here. Agreed? Wait, and here the electron concentration is more here and electron concentration is less here. Therefore, the electrons will diffuse from here to here. Agreed?
Yes.
See, in normal, this one, when I explained this to you, this hole, the hole here can attract an electron from here. Okay, that is, an electron will jump from conduction band to the valence band and this hole will attract it. That is something which I have explained. So here you see the motion is not because of diffusion. It is because what? It is because, you know, this hole attracts this electron and therefore it moves. Correct? So, in other words, there is an electric field created between these two. And because of this electric field here, the charges have been compelled to move and therefore, if at all a current results because of this motion, this current definitely we will call it as drift current. But here whatever current you are seeing here is because of diffusion. It's because of diffusion. So my dear friends, you have to appreciate and understand that the holes are moving from here to here. So there is a current in this direction. Okay, I will call it as IH. And electrons are moving from here to here. I will call that current as. Again, you see the direction of current is same in this direction only. And this current is what? The electron current. Now these two currents are not because of the electric potential or electric field. It is because of the concentration gradient, and I will call this as diffusion currents. Understood?
Yes.
Now, at the same time, there is a possibility that, well, the holes here are also attracting the electrons. There is a possibility, right? Because, okay, there is a possibility. I'll explain that around. And therefore, there is also another current that is flowing here, and that current is in this direction, and this current will be called as what? The drift current. Okay, So therefore, here you will find both the currents existing, but in opposite directions. Diffusion current and drift current. Now, so therefore, the process of diffusion will not be forever. A dynamic balance equilibrium is established. When the drift current will be equal to the diffusion current, then you see equilibrium is established. Did you appreciate this point?
Explain the cause of drift current.
I'll explain the cause of drift current. It's a very valid question. Okay, anybody else has any other question here? Hello? No question. Okay. Yeah, I'll drop this and once again I will explain this. Right. Now, there is P type of material and there is N type of material. So now, I will ask a basic question. What is a charged body? What is a charged body? Come on, quickly answer.
A body that either has an excess of electrons or a deficiency of electrons as compared to its neutral state.
Good. It's called charged body. Excellent. Now, is P type of material, what type of charged body is this? And N type of material, what type of charged body is this? Think and answer.
They are neutral materials.
Both of them are neutral. Agreed?
Yes, sir.
Why?
So because they are supposed, all the atoms have the number of electrons they are supposed to have.
So, that's right. So, the number of protons will always be equal to number of neutrons. Therefore, both of them are electrically neutral. Very good. Very well answered. Great. Okay. So, therefore, they are not charged. Okay. Well, I am going to form logical union of them. Now, you see, some holes, not all, some holes have drifted have diffused from here to here. Agreed?
Yes, sir.
Why did the holes go from here to here?
Because of attraction, sir.
Because of?
Attraction, sir, because they were attracted by higher density of electrons in.
See, if you use the wrong terminology, you are gone, case gentlemen. This is physics. Why did the holes move from here to here?
Due to difference in concentration.
That is the answer. Because of concentration gradient.
Yes, sir. Yes, sir.
So now, physically, so if a hole has moved from here to here, this becomes negatively charged and this becomes positively charged. Agreed?
Yes, that's it.
Physically it has moved.
Yes, sir.
And same way, concentration of electrons have moved from here to here. So an electron has moved from here to here, it will also create a positive, this will also become positively charged and this will become negatively charged. Correct?
Yes.
So physically you see there are more number of holes and less number of electrons. So this region now has become positively charged and this region, since the concentration of electrons have increased, number of electrons has increased and the number of holes has decreased, this becomes negatively charged. Agreed?
Sir, that whole P-type conductor will be negative.
You should not lower your loudness, you should maintain the same loudness. Please repeat once again.
That whole P-type conductor material will become negatively charged.
Correct, because hole is positively charged. Man, one positive charge from here has gone here. You first said both are neutral. So therefore, positive charge has gone from here to here, and therefore this is negatively charged. A negative charge has moved from here. This is negatively charged. This is positively charged. Correct?
Yes.
See, if anybody has got these fundamental doubts, clarify it now only. Don't say you will read it afterwards. You will absolutely don't have any time to read. I'm telling you, whatever you are learning today, that's the end of it. See now, still 2 chapters have to be completed. And then you will have lab examination. Still some more topics of first year are to be revised. Second year topics are to be revised. Your examinations may be announced in the month of February. So you hardly have any time for any sort of revision. So complete your learning in this class today only. Don't postpone it. If you have doubts, ask it. Okay, so did you understand now? Now I will say this is negatively charged body and this is positively charged body. Agreed?
Okay.
This is similar to a plate which is positively charged and this is similar to a plate which is negatively charged. Agreed?
Yes.
And therefore there is electric field from this side to this side. Agreed?
So, but then when there is creation of negative charge and positive charge, sir, why will it will stay like that?
Wait, it will not stay. I have not completed. See, you have to be very calm and cool, and you should learn with me. You should not try to go ahead and come behind also. You should go in phase with me. Understood? Then only you will learn. Otherwise, you will not learn. At every stage when I'm asking you, did you understand? You say that point you understood or not. Right? I will give you time to ask question. Okay, I see. Whenever you ask question, I have satisfied you. So now at this stage, I am explaining like this. Did you understand that this is analogous to a positive plate and this is analogous to a negative plate, and therefore there is electric field in this direction? Did you understand that?
Yes.
Okay, fine. Fine. You understood. Hello.
Yes, sir.
Good. Now here you see the holes are going from here to here. Holes, and holes are what? Majority charges here. Majority charges here. And here electrons are minority. Sorry, electrons in this region are majority charges. So the majority charges are diffusing, and therefore electric field is created. Agreed?
Yes.
Even though there are majority charges, here there are free electrons, there are also holes here, but holes are minority charge carriers. Agreed?
Yes.
And here what? Electrons are minority carriers.
Yes, sir.
Now what will this electric field do? This electric field, you see here, this electric field, those minority charges which are there here, this electric field will try to push these minority charge carriers towards this side. And this plate will try to push the electrons, minority charge carriers electrons from this side. Correct? So the electric field that is created here will do the other thing. What it will do? It will act upon the minority charge carriers in this way, and therefore, due to this electric field, there is a current flowing in this direction, and this current is drift current because of the electric field. And whatever current is flowing here is the diffusion current. And therefore, concentration gradient will do its job. It will create a diffusion current. चलो concentration gradient है, मैं charges बेचता हूँ, diffusion. और उस तरफ से बोलते हैं नहीं, मेरा electric field है, electric field जो negative charges उस तरफ है, मैं इसको इधर बेचूंगा. So the electric field will do its job, the diffusion current will do its job. So these two currents are going in opposite direction. At a particular point, this current will be equal to this current, and a balance is reached. That is called dynamic equilibrium. Did you understand this point?
After that, will it be dynamic equilibrium?
Yes, dynamic equilibrium. Why? Because you see, there is nothing like, okay, I sent so many charges, sir, you sent so many charges, sir, so let us have ceasefire. ऐसा नहीं रहता. ये डायनामिक इक्विलिब्रियम का मतलब क्या है? अभी आप दुर्गत भाई जाके देखा तो दुर्गत भाई, the market place, the number of people entering here and at the same time the number of people are coming out. So now if you measure at any time the concentration of people in Durgut Bhai, it will be constant. But that doesn't mean the number of people there are constant. Same thing is happening here. ये होते रहते हैं. ये जो नया होल्स उत्पन्न होता है, नया इलेक्ट्रॉन्स उत्पन्न होता है और रिकम्बाइन होकर विनाश भी हो जाता है और फिर से उत्पन्न होता है, फिर विनाश होता है, फिर से उत्पन्न होता है, फिर विनाश होता है। ये होते रहते और ये मसला तो चलता रहता है। ठीक है, दिस विल कीप कंटिन्यूइंग, बट फॉर अस व्हाट इज इंपॉर्टेंट इज एट अ पर्टिकुलर टाइम दिस करंट, the I diffusion current will be equal and opposite to, equal in magnitude but opposite in direction to the drift. And this is where we call it as dynamic equilibrium. Got it?
Yes, sir.
Okay? Okay, any questions here? This concept is extremely important here. This is the most important thing that you have to understand here. Because man, human being, he is able to use all the theories and explain this reality. He created the PN junction. The day PN junction is created, the whole revolution took place. You started getting small ICs, mobile phones, computers, chips, so many things. You see the digital world today. All because of the PN junction. And that important theory is what you are learning. Okay? So, this is the basic phenomena that takes place. Clear?
Yes.
Now, just to take you, make things clear. Intrinsic semiconductor, okay? N-type, P-type. So, CB. So, N-type you can see there are more number of electrons here, conduction band. As I said, you see when you add pentavalent impurity, you see here there are energy levels added below the conduction band. Can you see that?
Yes, sir.
When you add P-type material, energy levels are added here above the VV. So therefore, this energy gap, forbidden gap, is now reduced. The forbidden gap is now reduced. Can you appreciate that?
Yes, sir.
So for N-type, energy levels are created below the conduction band. For P-type, energy levels are created just above the valence band. And you can see the number concentration here is more for electrons, less for this. I mean, it is just shown in numbers. And here concentration of holes are more than this. I hope the diagram is clear to you.
Yes, sir.
Intrinsic, the concentration levels are equal. That's what I said. NH is equal to Ne. Now here, one more schematic. So here you see there is holes and electrons equal number. So here free electrons, okay, and positive donors. So ions are created. Very important. You see here free electrons are created, but you are creating an ion, a positive ion. Here you are creating a negative ion. Okay, because ions are going to play a role on the mobility. Current due to electron and hole. Current here due to both, but mainly due to electrons. Got it?
Yes, sir.
There will be current because of, see, in N-type also, there will be current due to holes and electrons. But it will be mainly due to the majority charge carriers, and those are electrons. Here, mainly due to holes. Here, Ne is equal to NH is equal to Ni. Ne is equal to NH is equal to Ni. The concentration of the free electrons is equal to concentration of the holes is equal to what is called as Ni is called intrinsic concentration for intrinsic semiconductor material. Got it?
Yes, sir.
At what temperature will this hold good? At what temperature will this hold good?
All temperatures, no?
Good. Good. That's it. At all temperatures. You use science and you answer. Right or wrong, you don't bother. That leave it to me. Here you see. NH is greater than Ne, as I told you. NH is greater than Ne. Okay? Hello? NH is greater than Ne. Right. So the whole concentration is greater than this. And for all practical purpose, Nd, what is Nd? The donor impurities. is approximately equal to Ne. The donor impurities is approximately equal to Ne. Very, very important concept.
Sir,
Ha.
also,
Ha.
the donor impurities will have their own electrons in the donated cell.
Ha.
And there will be some electrons which will
Ha.
come.
Good, good. You are a good boy. देखो ये डोनर इम्प्यूरिटीज क्या करता है? ओके, ये डोनर इम्प्यूरिटीज इलेक्ट्रॉन कॉन्सेंट्रेशन तो इंक्रीज किया. It has increased the electron concentration. Say it has created 1000 free electrons. See, assume I'm just giving a number. Don't write any number and write answers in the examination. See, there were 500 holes and 500 free electrons initially. Hello. Now you added a donor. You added some donor impurities. See, when you add donor impurities, it is not only the question of the number of the donor atoms. Okay, it is not only the question of number of donor atoms. Okay, it is also the question of this forbidden gap level being reduced. Okay, so therefore, some of the electrons which needed so much energy to go, with only little energy now it can cross over and become free electrons. Correct? Now, this donor, you know what it is? This donor, when you add, this is no longer creating the electrons. But now what happens? A fraction of this donor can nullify these holes. Hello, listen. Supposing I have added donor impurities, and that will also create 500 electrons. Assume.
Okay.
Now what? Out of these 500 electrons, say 250 of them will nullify the holes. So now holes become 250. Okay, and here this becomes 750.
Yes.
Okay, this becomes 750. Okay. Understood? See, this has also nullified the number of the holes. Nullified the number of holes. Now, if you see the simple mathematics here, okay, I have given you some number of 500 or something like that. It will definitely be more than this because the donor concentration will increase this by many times. Okay. Now, what you can see is here the concentration. See, now when you add donor, the concentration of the free electrons will be dictated by this. See, this Ne, what I wrote here 500, this is because of the thermally generated Ne. Correct? Now, by adding dopant, okay, I am able to control because now I am making what? The thermally generated free electrons and holes insignificant. And see, when you add donors, you are going to do this. So therefore, what this equation says is the concentration of the free electrons is completely controlled by the manufacturer, not by the Almighty. The nature is creating the thermally generated free electrons and holes. But now I am able to control the concentration. I will add how much ever dopant I want and I will get the required conductivity. Correct? And that is why we add the donor concentration to such an extent that this is much greater, this is much greater than this. Okay, and therefore I say I am able to control the conductivity. In Kannada, Aham Brahmasmi, I am the creator. Correct?
Yes.
And similarly here. Okay? Done. Now here, I is equal to IE plus IH. Here what happens? I is approximately equal to IE because majority carriers are responsible mainly due to electrons. Here, I is mainly dependent upon IH. Intrinsic semiconductor neutral. Quantity of electrons and holes are equal. Majority carriers are electrons, minority holes. Majority holes, minority electrons. I think this picture is quite clear and it has explained everything. Clear, students? Hello?
Yes, sir.
Right. Learn now, don't simply by heart. Now, we have been writing, the concentration of electrons, concentration of holes. It cannot just be some random numbers like that. Although the phenomena is random, there is a law which governs these two concentrations, or the concentration of holes and electrons are related. Now, that is called mass action law. In semiconductors, due to thermal effect, generation of free electrons and holes take place. Apart from the process of generation, recombination also occurs simultaneously, in which a free electron further recombines with a hole. It's a continuous process which I have explained. Okay, at equilibrium rate, the generation, listen here very carefully. At equilibrium rate, the generation of charge carriers is equal to the rate of recombination of the charge carriers. The recombination occurs due to E colliding the free electrons colliding with a hole. Larger value of Ne or NH, higher the probability of their recombination. Hence, I suppose you are following what I am reading here.
Yes, sir.
Hence, for a given semiconductor, the rate of recombination is proportional to Ne and NH. Or the rate of recombination is, it is Ne into NH. Rate of recombination is equal to some constant R into Ne into NH, where R is the recombination coefficient. The value of R remains constant for a solid according to the law of thermodynamics until crystalline lattice structure remains same. For intrinsic semiconductor, Ne is equal to NH is equal to Ni. So the rate of recombination is equal to R into Ni square, because Ne is equal to NH is equal to Ni, R into Ni square. So R into Ne into NH is equal to R Ni square, or Ni square is equal to Ne into NH. Okay, so you see here, very important. For intrinsic semiconductor, Ne is equal to NH is equal to Ni. And now you see, Ni square will always be a product of these two. Now, individually Ne can be greater than NH at some time. Now, read this very carefully. Under thermal equilibrium, the product of the concentration of Ne, free electrons, and the concentration of NH of the holes is a constant and is independent of the amount of doping by acceptor or donor impurities. See, I told you very clearly, even though you are adding the dopants, the thermally generated holes and electrons will happen the way it used to happen, irrespective. But the EG, or the forbidden gap, has decreased. Therefore, the concentration of these, or the number of these holes and electrons will increase. I hope you remember that statement. Hello?
Concentration constant there.
See, now read this very carefully. Under thermal equilibrium, the product of Ne and the concentration of NH of the holes is a constant and is independent of the amount of doping by acceptor and donor impurities. See, now understand this very carefully. See, here the value of R remains constant remains constant. For intrinsic semiconductor, Ne is equal to NH is equal to Ni. But for an extrinsic semiconductor, this is not equal. Hello?
What is Ni?
See, now become alert. Abhi ek intrinsic semiconductor lo, you take an intrinsic semiconductor. Have you taken an intrinsic semiconductor?
Yes, sir.
Okay, you take an intrinsic semiconductor. You have taken an intrinsic semiconductor. So in this intrinsic semiconductor, this will hold good, correct? Right? This will hold good at all temperatures. Now you do.
Ni means also this.
Yeah, you have taken an intrinsic semiconductor.
Yes, sir.
You have measured the number of hole concentration. You have measured the electron concentration, and you find that both of them are equal. And then you say this is equal to another number, the same number equal to Ni. That means what is Ne? A number. What is NH? A number. And this I am writing in general is equal to Ni. Ni stands for the intrinsic concentration. That means the concentration of holes or electrons at for an intrinsic semiconductor.
Okay.
Understood? The concentration of holes or the concentration of electrons of an intrinsic semiconductor is called Ni. Got it? Now, very important. Okay. Now, when you dope it, okay, when you dope it, or if the temperature increases, okay, when you dope it, what happens? Ne may be greater than Nh, or Nh can be greater than Ne. Agreed?
Yes, sir.
But you see the nature. This can be greater or this can be greater. But their product will always be equal to the square of the intrinsic concentration. This is the law.
Okay.
Understood? See, this is the law of the nature. आप जितना भी डोपिंग करो, ये जो इंट्रिंसिक concentration था, intrinsic concentration मतलब the concentration of the thermally generated electrons and holes, Ni, इसका square जो होता है, that number will be equal to the product of these two. So as you dope it, this can be greater or this can be greater, but this product will always be equal to this.
Sir, in that product, sir, that is also equal to Ni over intrinsic semiconductor, sir.
Ni of
Intrinsic semiconductor, sir. The value of Ni in intrinsic semiconductor. Will that be also equal to that doped semiconductor?
See, now you follow me. You see, if you go ahead of me, then you will have confusion. Then your time only will be wasted. मैंने क्या बोला? एक intrinsic semiconductor लो, और you determine its Ni. Did you do that?
Yes.
Now you dope it.
Yes, sir.
Now you dope it. Okay. Now when you dope it, see, I am not talking about the number of holes in the electrons. Now listen very carefully. I am not talking about capital N. I am talking about small n. I am not talking about the number of holes. I am talking about the concentration of holes in the electrons. Now when I dope it, either this will increase or this will increase depending upon the dopant. Correct?
Okay, yes, sir.
Supposing this increases, then this has to decrease.
Yes.
But their product will always be equal to Ni square.
Okay.
This is the law.
That Ni and that Ni are same.
Same.
Yes.
Same. See, you are taking intrinsic semiconductor at some temperature T. So at that temperature Ni is fixed.
Sir.
At that temperature if you dope it, Ne may be bigger than Nh or Nh may be bigger than Ne, irrespective. But their product at that temperature will always be equal to Ni square. That is the important thing.
Okay, yes.
See, now what happens here? See, for intrinsic, supposing this is 1000, this is also 1000. So this is also 1000.
Yes.
Now here you see, here 1000 ka square will be 10,000.
Yes.
So this will be 10,000 means this can be 100.
Not 10.
What is it? 10,000 into 1,000? No? 1 million. 1 million. This is 1 million. Okay.
Yes.
Now you see, when you dope it, this can only become 100. Then this will become 10,000.
Yes.
But this will still remain 1 million.
Correct.
Understood? So what it means here is, by doping, if you increase one of the concentration, not only that concentration will increase, but the concentration of the minorities will automatically decrease based on this law.
Okay.
That's the idea.
Yes.
Got it?
Yes.
Good. Any other question? Very important here. See, if you understand these basics properly, you can answer the questions. Otherwise, you will not be possible to answer any questions in mains and NEET. And leave that aside. You will never become good engineers and good professionals. Okay, shall I continue?
Yes, sir. Yes, sir.
Yes. Now, this is another important phenomena that takes place. Electron-hole recombination. Now, it is necessary to complete a bond that electron is shared from neighboring atoms, or it may also be received from conduction bond. To complete a bond, see, the electron is shared from the neighboring atom, or it may also be received from the conduction bond. That means now, for a bond to be completed, you need the number of electrons, right? So these electrons will be shared from the neighboring atom, or it can also be received from the conduction bond. In the second case, electron recombines with the hole of the valence bond. This process is known as electron-hole recombination. In other words, when there is a tendency to form a bond, okay, there are two things that happen. Yes, all of us have studied in chemistry that there is atomic interaction between two atoms. Agree. What is that interaction? So something is attracting something, isn't it? So here you see, so for an electron, for the bond to be formed, it needs electron. That means if the electron is somewhere, so this bond here, see that the concept of hole here is that it creates an energy level to attract an electron and fill up the bond. That's the idea behind this. And when that happens, we are using the word electron-hole recombination, especially if the electron comes from the conduction band and occupies the valence band to complete the bond. That is called electron-hole recombination. Okay? The breaking of the bonds or generation of electron-hole pairs and the completion of bonds due to recombination is taking place continuously. At equilibrium, the rate of generation becomes equal to the rate of recombination, giving a fixed number of free electrons and holes. So something which I explained is put in proper words. You can read it again. If you have some doubt, you ask. Clear?
Yes.
Now, the most important thing. What is a PN junction diode? See, you have got other types of diodes. I will not now. Don't ask me what are the other types of diodes. I don't want to get deviated. But just let's concentrate on PN junction diode. PN junctions are itself called diodes because they allow the flow of current in one direction and not in another direction, and also because there are two terminals or distinct electrodes. One is anode and cathode, ode. That anode and cathode ka ode diya, and there are two electrodes, okay, and they are allowing current to flow in only one direction. That is why the name diode has come into picture. Okay. Metallurgical union of P type of semiconductor with N type of semiconductor material with two non-rectifying electrodes is called PN junction diodes. Now, what is this non-rectifying? I'll explain. Okay, please remember that. I'll explain. So, what is PN junction? Metallurgical. I have already explained what is metallurgical union. Correct? Hello.
Yes, sir.
Metallurgical union of P type of semiconductor with N type of semiconductor material with two non-rectifying electrodes is called PN junction. PN junction, when metallurgical junction is formed between a N type and P type semiconductor, majority charge carriers diffuse across the junction, leaving behind opposite fixed charge and creating an electric field. This process continues until fixed charge remains for the carrier drift to balance the carrier diffusion. I have explained these statements also. Only thing new is the definition of the PN junction diode. Clear?
Yes.
Okay, so somebody asks you what is a PN junction, you should write this golden definition. Okay? You will really be appreciated. Done. Shall I move on?
Sir, two non-rectifying.
See, you are again not listening to me, you are not learning with me. You please learn with me. I told you I will explain that later on. I need to first explain what is rectification. That itself will take one full class. And then I will once again come back to this definition and you will understand. Okay? ऐसा कुछ है? हाँ, अभी एक न्यूमेरिकल है, सभी लोग सॉल्व करो इसको. Everybody solve this. The energy of a photon. हाँ, solve. The energy of a photon of sodium light so and so equals the band gap of semiconductor. Find the minimum energy E required to create an electron hole pair. The value of E by kT at a temperature. Lambda is given. They have written C. They have written the word energy. Energy, photon, sodium light, wavelength is given. Equals the band gap of semiconducting material. So you should know Eg for the semiconductor material. Find the minimum energy required to create a whole electron pair. So if I give you the wavelength, hello, can you now tell me what is the energy of the photon?
Yes, sir.
Tell. E is equal to h nu. E is equal to h by lambda.
Yes.
Isn't it? Hc by lambda.
Yes, sir.
Hc by lambda. So you can calculate the E there, and that E is the energy equal to the forbidden gap. Isn't it?
Yes.
So what it means is, if you are able to pass this photon to the intrinsic semiconductor or the semiconductor material, and if an electron absorbs this, right, then it can kick the electron from the valence band to the conduction band. That is this minimum energy to supply. So I hope you can find it. Right? That is first part. Then the value of E by kT at room temperature 3. So you have to use that formula. Right? A T to the power of 3 by 2 into E raised to minus Eg by kT. So you can find the value of E by kT. Okay?
So that is for N also. N.
That is to find the number of electrons, correct? The number of electrons that are passing through, that are moving from this point to that point. Okay. The value of E by kT. You consider one electron and do that? No.
Is that kT?
Okay, the first part you calculated.
Yes. Yes.
So plug in the value, right? Nanometers, angstrom. Then E is equal to, so by this one, so E by kT. Just substitute the value. That's it.
KT.
Boltzmann constant, man.
Okay.
They have asked you E, you see K. That is a problem, man. See, we use K for different things, no? So K is used in mechanics for radius of gyration, and K is also used for spring constant. So many problems. So in this context, K means Boltzmann constant. And you can see now this number 1.38 into 10 to the power of minus 23. By this you should understand it. So they are calculated E in terms of electron volts. We have already done such problems. So you see the same thing is used here. Okay? Hello?
Yes, sir. Yes, sir.
Done.
Yes, sir.
Okay.